Entire screen.
Yes.
Can you see?
Yes, sir.
Can you see
Great.
my?
Yes, sir.
Now you see?
Yes, sir.
All right. There is some point,
Okay.
some problem with my opening that video. So no problem. I will. Okay.
Okay. Madam, we can start. No, sir.
Yes, sir.
There will be a need. Welcome, and then after that you can start. Sir.
Welcome, Joshipura. Hello.
Joshipura, sir.
Yes.
So good evening, everyone. Good evening,
Oh.
each one of you here. A very warm welcome on behalf of Indian Association of Physics Teachers. Very happy to have a second webinar in the series of IYQ by Indian Association of Physics Teachers. The first of the webinar, that was a curtain raiser, which was organized by RC07 Gujarat Regional Council. And we have now a second organized by RC14, which is Kerala Regional Council. So for this, let me welcome each one of you. Today's speaker, VPN Nampuri, the president of IAPT, Professor P.K. Aluwalia ji, past president, Professor K. Joshipura ji, Professor Ghatak, Professor Ajit Prasad, who is the president of RC14, and all the dignitaries present here. Of course, there are many, everybody is here a very respectable member of IAPT. So I welcome each one of you and request Professor Dr. Ajit Prasad, who is the president of RC14 Kerala, to accept the chair for this particular session. The guest speaker for us today is Professor VPN Nampuri. He is going to talk on SN Bose. We are going to have the very important webinar, which is going to discuss the shining stars of Indian science, that is the contribution of Indian scientists towards the quantum mechanics, being a year of IYQ 2025. So let me welcome Dr. Ajit Prasad to take the chair and proceed further for the session. Dr. Ajit Prasad.
Thank you, madam. It is with a great pleasure and pride I take this occasion, because my teacher and research guide, Professor Namburi sir, is delivering the lecture on C.V. Raman. S.N. Bose. I know him from the days from my PG classes in Cochin University, and he's a great teacher. He's a good academician, and he has guided 68 students to successfully complete their PhD work, and more than 700 publications are there in his credit. And in fact, he was an inspiration to so many students in the research laboratory for pursuing their research activities there in the Cochin University. And now it is a center of vigorous or serious research activities, especially in the physics department as well as in the International School of Photonics. And he has adorned many positions in his career. Even now, he is pursuing his interest in the realm of research. And in fact, when we are Kerala, considering the Kerala scenario in general, his position as a physicist, as a researcher, as a teacher, it is very important, paramount. So, in fact, he is relaying the mantle from Professor C.V. Raman. His guide, Professor M.M. Patel, was the student of P.S. Narayanan, and Professor P.S. Narayanan was student of C.V. Raman. and so many other students are there to lay the and take over the mantle to pursue the research activities started by C.V. Raman when he was in Calcutta. So now I invite Professor Nambedi sir to deliver his talk on Asian box.
Thank you, Dr. Ajit Prasad. I am also thankful to IAPT and other office bearers for giving me a chance to talk on the legacy of Satyendranath Bose, especially when the so-called God particle Higgs boson was discovered at CERN. So let me start straight away without losing much time. As a prologue, first half of the 20th century witnessed the creation of two pillars of human knowledge and related paradigm shifts and knowledge revolutions. In the microscopic world, quantum mechanics, and in macroscopic world, theory of relativity. Theoretical formulations related to quantum mechanics have the presence of three quantum Indians, Meghnath Saha, Satyendranath Bose, and C.V. Raman, among whom one brought Nobel Prize to India and to Asia in physics. I am audible?
Yeah,
Sir?
sir. Certainly.
Okay. Later on, during the second half of the century, Indians challenged the existing theories of quantum mechanics and the theory of relativity by scientists like E.C.G. Sudarshan, Tanu Padmanabhan, C.S. Unikrishnan, laying foundations to quantum optics, general theory of relativity as a thermodynamic problem, and C.S. Unikrishnan reformulating special theory of relativity based on Galilean transformations. Another scientist, Dr. Manoj Kailath from Amrita University, Coimbatore, who shakes even the foundations of chemistry through his insights in the role of oxygen as a life support. Let me start at the threshold of universe creation, a brief history of God particle and the legacy of Satyendranath Bose. Formula for blackbody radiation has been derived in three independent ways by Max Planck, Einstein, and S.N. Bose. All three approaches, as a bonus, gave birth to two new branches of studies: Planck's quantum theory, Einstein's A and B coefficients to introduce stimulated and spontaneous emission of radiation, leading to basic theory of lasers to be invented about 4 decades later, and quantum statistics leading to Bose-Einstein condensation. Bose-Einstein condensation was later on realized in the laboratory, for which the Nobel Prize was awarded. Formula for blackbody radiation has been consider an atom beam is irradiated by a counter-propagating laser beam with frequency slightly redshifted. Moving atoms will resonantly absorb the radiation due to blue shift effect. Repeated absorptions of photons by atoms reduce the velocity of atoms, thereby cooling the atom beam. Decrease in velocity introduces reduction in Doppler shift. When velocity is reduced to 6 meters per second, corresponding to 240 microkelvin temperature, no further cooling by Doppler shift is possible since the atoms go out of resonance. Cooling of atoms beam through repeated absorption of lasers led to the discovery of Bose-Einstein condensation. About 2000 rubidium atoms are condensed to lowest energy state at about 100 millikelvin temperature. Bose-Einstein condensate make 2000 atoms behave like a massive atom with almost zero mobility in the trap. Satyendranath Bose was a legend in his own lifetime. In 1924, from Dhaka, essentially a place nowhere in the scientific world, he wrote a brilliant paper that confirmed Einstein's contested view of photon. It showed that photons are not ordinary particles, but are strange entities that tend to flock together following a different kind of particle statistics. Einstein read the paper and, pleased by his unexpected support of his ideas, applied Bose's method to ideal gases, laying the foundations of quantum theory of gases. The new physics came to be known as Bose-Einstein statistics. Abraham Pais, a physicist and biographer of Einstein, noted There had been no such successful shot in the dark after Max Planck introduced the quantum in 1900. Bose's paper was the last of the four revolutionary publications since that completed the old quantum theory and led to the new mechanics, others being those of Planck in 1900, Einstein in 1905, and Niels Bohr in 1913. The three quantum persons from India, three extraordinary physics discoveries were made in colonial India, which did not have any tradition of research in modern physics. Saha ionization equation, Bose statistics, and Raman effect. All three discoverers were founding faculty members of new small physics department of Calcutta University, which started functioning in 1916. These discoveries were all on the general topic of interaction between light and radiation. Bose was born in January 1, 1894 in Calcutta. A galaxy of brilliant and rebellious men appeared on the scene, embracing Western learning and science from an essentially Indian standpoint. Bose's family was drawn into that movement, and his father, Surendranath, had his own chemical and pharmaceutical industry. The unrest was becoming uncomfortable for British, and in 1905, when Bose was only 11, Lord Curzon, the British Viceroy, divided Bengal into two parts. Bose's father instructed his only son not to get involved in political movement or attend any musical events. He obeyed the first instruction, but quietly disobeyed the second. Bose's mathematical abilities first became evident when he was in upper classes in school. His mathematics teacher once gave him 110 out of 100 marks on a class test. He had answered all the questions correctly and in some cases showed more than one method to get to the answer. The teacher predicted that Bose would one day be known as a great mathematician. Bose subsequently joined the prestigious Presidency College, where his professors included Jagadish Chandra Bose, discoverer of microwaves and a pioneer in plant electrophysiology, Professor Chandra Roy, known for his work with mercurous nitride and as a great teacher, historian, industrialist, and philanthropist. Among Bose's classmates was Meghna Saha, who went on to do pioneering work in astrophysics. Saha was the first to apply Bohr's theory of atoms to calculate the temperature, pressure, and chemical composition of stars from the degree of ionization of atoms near their surface. This work provided an explanation for why the stars seem to have completely different chemical compositions depending on their size and temperature. Bose and Saha became great friends. They studied mathematics together and eventually appointed assistant lecturers in physics at newly established University College of Science and Technology. In Einstein and other European scientists, Calcutta founded in 1914. The pair had learned German, French, and English so that they could study the papers that were being written by Planck. A momentous event in physics occurred following the total solar eclipse of May 29, 1919, when Arthur Eddington observed the diffraction of starlight passing near the sun. His observation was supported Einstein's prediction for gravitational bending of light. After this event, Bose and Saha translated all of Einstein's and Hermann Minkowski's papers from German into English to introduce latest in theoretical physics to the students. The translation of the work of Bose and Saha was published by University of Calcutta in 1920 as a volume entitled The Principle of Relativity, with an introduction by Professor P.C. Mahalanobis, a friend of Bose and Saha, who would go on to become a pioneer in statistics in India. In fact, this was the first translation of Einstein's papers into English. Bose and Saha wrote their first research papers together on equation of state for real gases. Saha then went abroad to work with Ralph Fowler in England, where he would further develop his theory of thermal ionization, while Bose joined the newly established University of Dhaka as a reader in physics. It was while teaching quantum theory in Dhaka that he first noticed a logical problem in all known derivations of Planck's law of blackbody radiation. The problem was further accentuated when Zaha drew his attention to Pauli's derivation of the law, which had just appeared in print. It presented a conjectured probability of electron-photon scattering that depended on both the initial and final states, something that appeared crazy at the time. Bose was grappling with this problem sometimes between late 1923 and early 1924 when he hit upon his great idea. Bose succeeded in deriving Planck's formula free of any logical difficulties by treating blackbody radiation as a gas of photons with new statistics. Unable to get his papers published in philosophical magazine, Bose sent it to Einstein with a humble request to have it translated into German and published in a reputable German journal. Einstein was, of course, delighted at this unexpected confirmation of his photon idea, albeit adopted by Bose to take account of its correct statistics. Einstein translated the paper himself and got it published in Zeitschrift for Physics with a translator's footnote. In my opinion, Bose's derivation signifies an important advance. The method used here gives the quantum theory of an ideal gas, as I will work out elsewhere. Thus began the writings of Einstein's seminal papers on new statistics. In communication to Prussian Academy in Berlin on July 10, 1924, January 8, 1925, and January 29, 1925, he extended Bose's method to ideal gases and predicted the Bose-Einstein condensate, a form of ultra-cold matter that would not be observed until 70 years later. On the afternoon of Sunday, October 7, 1900, Rubens had tea with Planck and told him about the latest experimental data on blackbody spectrum that he and Kuhlbaum had obtained. After Rubens left, Planck set about finding a mathematical formula that would fit the data. He succeeded with his formula, incorporating the new fundamental constant h with the dimension of action. Clearly, some theoretical justification for it was required. Planck tried very hard and finally, as an act of desperation to obtain a positive result under any circumstance and at whatever cost, he introduced the concept of irreducible packets or quanta of energy for the material in the oven walls, not in radiation itself. In mid 1900, December 1900, he presented a statistical derivation involving a distribution of the energy quanta among the hypothetical wall of resonators. It had no more justification than it gave the desired result. On the Einstein appeared on the scene in 1905. He used Wein's result on the entropy of radiation to calculate the volume dependence of entropy of thermal radiation. He drew the revolutionary conclusion that in monochromatic radiation of low density within range of validity of Wein's radiation formula behaves thermodynamically as if it consisted of mutually independent energy quanta of magnitude r beta nu by n. The factor r beta nu by n equals h nu. Thus was born the great idea of light quanta, now called photons. Einstein applied this principle to three empirically known phenomena: the Stokes rule in photoluminescence, the photoelectric effect, and ionization gases by ultraviolet light. Among these, the application to photoelectricity was drawn the most public attention as it eventually led Einstein to Nobel Prize. But Einstein's idea of mutually independent energy quanta had its own problem. It clashed with Planck's law and therefore with Planck's distribution W, which required indistinguishable and correlated quanta, not mutually independent quanta. Most physicists were skeptical of light quantum hypothesis even after Robert Millikan's detailed work on the photoelectric effect verifying Einstein's simple equation. Millikan himself remarked in his 1916 paper, yet the semi-corpuscular theory by which Einstein arrived at this equation seems at present to be wholly untenable. The main problem was how to account for the well-established wave properties of radiation in terms of light quanta. The prejudice was so strong that even Planck, Rubens, Nernst, and Warburg, who were keen to bring Einstein to Berlin, felt compelled to write to the Prussian Ministry of Education. That he may sometimes have missed the target in his speculation, as for example, in theory of light quanta, cannot really be held against him. Bohr too was opposed to light quantum idea and avoided using it in his 1930 paper on atomic model. Following Planck quite closely, he introduced transition between the stationary states of atoms, giving rise to absorption or emission of classical radiation, whose frequency were determined by the relation nu is E1 minus E2 by h. Contrary to what usually stated in textbooks, he made no mention of light quanta. Strong experimental evidence in favor of light quanta eventually emerged in 1923 from Coulomb effect. The classical wave theory of radiation failed to explain the observed shifts in the wavelength of the scattered X-rays. Observation clearly pointed towards the elementary processes of energy transfer between light quanta and electrons in the atom. Although empirical evidence in favor of light quantum hypothesis was mounting, its theoretical basis remained unsatisfactory on three accounts. One, there was a fundamental conflict between statistical independence of Einstein's light quanta and the Planck law. Two, there was no logically satisfactory derivation of Planck's law despite several attempts by leading physicists, including Planck himself, as well as Einstein, Ernst, Pauli, and Debye. All these attempts, ingenious as they were, suffered from one drawback. In all of them, the first factor in Planck's law, 8 pi nu squared d nu by c cubed, was always taken from classical electrodynamics to be the number of modes of vibration of radiation in unit volume. These authors reduced the second factor in different ways by postulating ad hoc rules for different elementary processes. 3. All these attempts used Planck's hypothesis that quantizing was restricted to exchange of energy between radiation and matter, but the Compton effect had shown that radiation itself consists of energy quanta. Both considered the probability distribution of n indistinguishable photons in G cells in six-dimensional phase space dx, dy, dz, dpx, dpy, dpz. Smallest volume in phase space possible can be written as dx dpx, dy dpy, dz dpz, which is hq. So we have phase space volume of a single photon G as integral dx, dy, dz, dps, dpy, dpz, which is integral v, dps, dpy, dpz. By remembering E by C, which is h nu by C, as p squared is px squared plus py squared plus pz squared, which is h squared nu squared by c squared, integrating p to p plus dp, d of 4 pi by 3 p cube, which is 4 pi by 3, integral p to p plus dp, d of h cube nu cube by c cube, which is 4 pi by 3 h cube by c cube, 3 nu squared d nu, from which we get G as V 4 pi nu squared S cube by C cube dV. Then number of cells per unit volume to attribute two polarization states. We multiply the RHS by 2 so that the number of cells per unit volume will be 8 pi nu squared by C cube to d nu. Story goes like when Bose was teaching in Dhaka College on probability distribution to get head and tail while tossing two identical coins. Probabilities of getting events HH, TH, HG, TT were calculated by taking TH is equal to HG. Since the coins are indistinguishable, Bose wrote probabilities to get three events HH, TT, TH as 1 by 3 each instead of 1 by 3, 1 by 4 as classical probability state described. In 1924, Bose solved all these problems in one stroke by deriving the full Planck law, including the first factor from quantum theory. The first factor then emerged as the number of irreducible cells in phase space of the photon, that is, the number of quantum states of photon, and hence the number of possible arrangements of a photon. Thus, the quantum states of the photon are distinguished only by the number of photons in each state. This fact immediately implies that photons not merely hypothetical resonators in the wall, are indistinguishable. The entire physics becomes transparent. To arrive at the expression for the cell density in phase space without invoking the mode density from electromagnetic theory is a remarkable success of Bose, apart from describing photon as real indistinguishable particle as early as 1924, before the rise of quantum mechanics. He also calculated the probability density W of for n indistinguishable particles like photons in G cells in the phase space volume as W n G n particles in G cells as n plus G minus 1 factorial by n factorial to G minus 1 factorial. For example, W 34 in Bose-Einstein will be 20. In 1926, Dirac and Fermi obtained for particles like electrons obeying Pauli's exclusion principles as W F D as G factorial by n factorial G minus n factorial, or WFD 34 is 4. on, on June 4, 1924, Bose wrote to Einstein, I have ventured to send you the accompanying article for your perusal and opinion. I am anxious to know what you think of it. You will see that I have tried to deduce the coefficient 8 pi nu squared by c cube in Planck's law, independent of classical electrodynamics, only assuming that ultimate elementary regions in phase space have the content H. Einstein, in letter to Enfast, dated July 12, wrote, the Indian Bose has given a beautiful derivation of Planck's law, including the constant 8 pi nu squared by c cube. Nonetheless, the derivation of the first factor had led to be supplemented by a factor 2 due to the two states of polarization of light, which were not wholly quantum mechanical. Einstein observed in a postcard to Bose dated July 2, Dear colleague, I have translated your work and communicated to Sage for Physics for publication. It signifies an important step forward and I liked it very much. Factually, I find your objections against my work not correct, for Wayne's displacement law does not assume the wave theory and Bohr's correspondence principle is not at all applicable. However, this does not matter. You are the first to derive the factor quantum theoretically, even though because of the polarization factor 2, not wholly rigorously. It's a beautiful step forward. With friendly greetings, U.S. Albert A. Einstein. The translation of paper of Einstein. This is a translation of paper appeared in 1924. It seems this paper has never been translated in English so far. In this paper, Einstein developed for the first time the Bose-Einstein statistics, applying the idea first described in a paper by D. Bose and extending them to massive particles, here called atoms or molecules. In 1925, Einstein published a second part of this paper, and in which he investigated, among other, the existence of what is now known as Bose-Einstein condensate. Except for the abstract footnotes in italics and final acknowledgement, all the text is from the original paper. The equation numbering does not confirm the original one. A quantum theory of ideal gas free from arbitrary ansatz does not even exist today. This gap will be filled in the following on the basis of new approach proposed by Mr. D. Bose, from which that author has obtained a most remarkable derivation of Planck's radiation formula. The method following Bose can be characterized. Remember that he even misspelled S.N. Bose because he was familiar with Dr. D. Bose, who was a researcher in Germany. Many years later, Bose confided to one of his friends the following story. You know, my deduction of Planck's law had a factor of 2 missing. So I proposed that it came from the fact that photon had a spin and that it can spin either parallel or anti-parallel to its direction of motion. That would give the additional factor 2. But the old man crossed it out and said it was not necessarily to talk about spin. The factor of 2 comes from the two states of polarization of light. Then he smiled mischievously and said, I can understand a spinning particle, but what is the meaning of polarization of a particle? When it was pointed out, when photon spin was eventually discovered, why didn't you tell Einstein that you had discovered it already in 1924? No doubt, a person like Einstein would have stood by you and you would have surely won a Nobel Prize. Looking calmly, he replied, how does it matter who discovered it? And then, with a sense of triumph, he said, it has been discovered, hasn't it? In 1931, C.V. Raman and S. Bhagavandam in the Indian Journal of Physics published a paper with the title Experimental Proof of Spin of the Photon. It reads, in its well-known derivation of Planck's radiation formula, quantum process Sn for the number of cells in phase space of and found himself obliged to multiply it by a numerical factor 2 in order to derive it from correct number of possible arrangement energy and linear momentum s nu by c, also an intrinsic spin or angular momentum plus or minus s by 2 pi round an axis parallel to the direction of its motion. The paper was published, did not contain a detailed discussion of the necessity for the introduction of this factor, but we understand from a personal communication by Professor Bose. The weight factor 2 thus arises from the possibility of spin of quantum being either right-handed or left-handed, corresponding to the two alternative signs of the angular momentum. C.V. Raman's experiment conclusively showed that Bose's view was the correct one and provided the first experimental measurement of the photon spin. This fact is hardly known to scientists and historians of science. One of the first effects of Bose's publication was that British physicist Paul Dirac coined the word boson for the class of quantum particles that follow Bose-Einstein statistics. Aside from bosons, there is only one other class of quantum particles, fermions, which were discovered by Fermi and Dirac. Bosons and fermions follow two types of quantum statistics, the Bose-Einstein statistics and Fermi-Dirac statistics, respectively. Since the original idea for the statistics of quantum particle came from Bose, Dirac chose the name of the particle following Bose-Einstein statistics as bosons. In his modesty, he named the other type fermions. These appellations appeared for the first time in Dirac's classic monograph, The Principles of Quantum Mechanics. There's an interesting story about Dirac's visit to Calcutta to meet S.N. Bose. Bose and his students received Dirac and his wife and took them to the hotel in Bose's car. Dirac and his wife occupied the back seat in the car. Bose and his students occupied front seat, which was overcrowded. Dirac invited some of his students to sit in the back. Bose, unwilling to cause inconvenience to Dirac and Mrs. Dirac, remarked, "We believe in Bose statistics, which allows overcrowding of particles in quantum state, and Dirac in Fermi-Dirac statistics." It turns out, crucial difference between bosons and fermions is that while any number of identical bosons can occupy the same quantum state, two or more identical fermions cannot occupy the same quantum state. The clannish behavior of bosons is responsible for Bose-Einstein condensation. Bosons are the field particles representing the interaction between particles, and bosons have intrinsic spins that are ns bar with n equal to 0, 1, 2, etc. Fermions are material particles and have no integer values of spin and momentum, n plus half s bar. This is known as spin statistics theorem. Thus, the fundamental building blocks of universe are of two types, namely bosons and fermions. According to the standard model of particle physics, leptons, which are the electrons, the muons, tauons, three neutrinos associated with the leptons and their antiparticles, six quarks and their antiparticles, are all fermions. The quantum excitations of the field that mediate interaction are all bosons. Examples include the photon, which mediates electromagnetic interactions. The W and Z particles which mediate weak interactions such as radioactivity, and gluons which bind quarks to form hadrons such as neutrons, protons, and pions. As a unique member in the class of boson particles, to understand the universe is Higgs boson, which is the field particle or quanta or strong interaction field between quarks predicted by battery physicist Peter Higgs. Higgs boson was discovered during an experiment conducted at CERN facility called Large Hadron Collider in Europe. What is the importance of Higgs bosons? Physics describes the world of fundamental particles using what is called standard model. However, it does not describe how particles get their mass, which is one of the important fundamental properties of particles. Why particles like photons do not have mass, while electrons have only small magnitude of mass, and protons as well as neutrons have larger mass. Peter Higgs hypothesized the existence of a boson particles called Higgs boson, which gave property of masses to the particles. In this respect, Higgs bosons can be treated as the important partner in the threshold of universe creation. This as though standing behind the Higgs boson and looking over its shoulders, we witness the universe in the process of getting created. Following the sections of the article will lead the readers to the experience, the thrill of events which took place at CERN on the event of detection of Higgs boson. From time immemorial, the wide spread of cosmos and millions of stars, planets, and satellites are sources of wonder in human mind, creating quest to know their secrets. Our universe contains multitudes of different objects which make our everyday life happy and comfortable. Scientists explored the possibilities of matter constituting of few number of elementary particles, knowledge of which will be useful to physicists and chemists. Till 1930, there were only three such particles, namely electrons orbiting around the nucleus and protons and neutrons inside the nucleus. However, as the methods of theoretical physics and instrumentation techniques improved, new particles emerged, and it was found that there are only two classes of particles called leptons and quarks. Nuclear particles, protons and neutrons, are made up of up and down quarks. According to standard model, universe is made up of six leptons, electrons, mu meson, tau lepton, electron neutrino, muon neutrino, and tau neutrino. And six quarks, up, down, strange, charm, beauty, top, along with their antiparticles. In short, all materials of the universe are made up of 12 type of particles and their antiparticles, along with three field particles. For example, proton is made up of two up and two down quarks. That is, P is UUD, so that total charge of P is +1. Similarly, neutron has a quarks model DDU with total charge 0. Quarks inside nucleons are under the influence of strong force due to strong field, gluon field. With gluon are the field particles of strong force, like photons, the field particle of electromagnetic field. If m is the mass of field particle, then the range of influence of force can be calculated as r is h by mc, where r the range of force, h is Planck's constant, and c is velocity of light. For example, in the case of electromagnetic field and gravitational field with field particle photon and gravitons, respectively with zero mass, will make respective ranges infinite. Hence, two galaxies, even at millions of light years apart, will experience mutual gravitational force. Protons and neutrons with mass 1.7 into 10 to the minus 27 kilogram will experience nuclear force within nuclear range, while electrons with a mass 9 into 10 to the minus 31 kilogram will have the force range within the atom. In the case of nucleons with mass of the order of giga electron volt, will have the range of strong force with the size of nucleons, namely proton or neutron. Hence, quark-gluon interaction is so strong that quarks are confined within the nucleon space, and hence the independent quarks have not yet been discovered. As noted earlier, Peter Higgs predicted the existence of boson particle known as Higgs boson, interaction of which with particles will give the property of mass to the interacting particles. depending on whether the speed of interacting particles change their speed or not. For example, gravitons and photons do not change their speed during their interaction with Higgs boson, so that they have zero mass, whereas electrons and other particles suffer speed reduction and hence they acquire mass. Experiments to detect Higgs boson are carried out at CERN, details of which will be outlined in the following sections. Detection of Higgs boson brought Nobel Prize to Peter Higgs in 2013. He died as the most satisfied scientist by witnessing a theoretical prediction getting confirmed by experiment at CERN. We will briefly describe the details and working of Large Hadron Collider in CERN and how it helped to trap his particle. The LHC experiment at CERN is the largest international collaborative experimental setup in nuclear and particle physics with 176 research and university institutions from 38 countries involving about 3,000 scientists, 1,000 research scholars, and large number of technical assistants. Discoveries in LHC experiment by tracking down Higgs boson generated so much interest all over the world due to belief that man has reached at the threshold to watch the creation of the universe. India donated a tall statue of Shiva Tandava, which stands majestically in the front quadrangle of CERN, representing the flow of high energy causing the creation of universe, a symbolic representation of experiments going on in CERN. The LHC is about 100 meters below the Earth's surface with circular vacuum metal tube of 27 kilometers circumference. Basic principle of LHC experiment is that head-on collision between particles at higher energies will smash them to reveal the internal structure of the particles. Initially, cosmic rays were the only source of elementary particles to study their interactions and particle collisions. By photographing the cosmic ray showers from atmosphere, scientists were able to discover new particles, including antiparticles like anti-electrons called positrons predicted by Dirac. However, scientists were not able to tune the cosmic ray particles at high energies. In order to solve this problem, scientists developed various types of particle accelerators to increase the energy of particle collisions. In the conference room at LHC facility, Peter Higgs was presented in the front row to witness the historic declaration of discovery of Higgs boson. He was so emotional that he said, "It is so important be present and hear the success of theoretical prediction through experimental confirmation. I did not even dreamt of the situation of discovery of Higgs boson in my lifetime." Second of such emotional outburst came when scientists discovered the gravitational waves generated through black hole collisions. These are the two events in the history of science which are important in revealing secret of the universe several years after their theoretical predictions. Unfortunately, since posthumous Nobel Prize cannot be awarded, S.N. Bose missed the Nobel Prize. This is the elementary particle structure and including the Higgs boson discovery and standard model. The Indian presence of prediction of boson particles are still more important in history of science. When S.N. Bose described the light particles, photons, he attributed them as particles with integer spin 1, with two components, +1 and -1 for clockwise and anti-clockwise polarizing light beam. When Einstein modified the manuscript of the paper of S.N. Bose, Einstein did not approve the photon spin as described in the paper corresponding to RH and LH polarized light beam. The paper was published without mentioning the photon spin. If Einstein did not stroke off the photon spin from the paper, S.N. Bose could have been the physicist who introduced the particle spin in quantum mechanics instead of Pauli, to whom discovery of particle spin property is attributed, followed by exclusion principle. Had time supported S.N. Bose, then he could have been discoverer of exclusion principle, and the history of quantum mechanics could have Bose's exclusion principle instead of Pauli's exclusion principle, renaming fermion particles as half-integer Bose particles. One should accept the fate of history of science just as the fate of human species. Bose felt sad that Einstein did not find the core of his arguments regarding the photon spin. For the next 12 years, Einstein published his papers. Bose did not do any research except teaching. When 1 century of quantum statistics is elapsed, one should remember that Satyendranath Bose could have brought second Nobel Prize in physics to India had Einstein did not strike photon spin in the article of Bose entrusted to Einstein. He did not even discuss the topic with Bose, but fate has its own design. Higgs boson was intrinsic in understanding of how lepton mass was generated in Big Bang. In 1964, Penzias and Robert Wilson, working with horn antenna at Bell Labs in Princeton, accidentally discovered cosmic microwave background radiation, which is strong evidence in favor of a hot early universe as implicated in Big Bang theory and against the rival steady state theory. For this landmark discovery, Penzias and Wilson were awarded the 1978 Nobel Prize in Physics. It turns out that according to the precision observations carried out in 1994 by Far Infrared Absolute Spectrophotometer abroad in Cosmic Background Explorer satellite, cosmic microwave background radiation has pure Planck spectrum, signaling that it is blackbody radiation in thermal equilibrium at a temperature of 2.7 K. It was precisely the spectrum of blackbody radiation measured in labs in the last few years of 19th century that led Planck to discover quantum theory in 1900. And it was this Planck spectrum that led Bose to discover the new statistics in 1924. At first, Bose's new statistics seemed outlandish to everyone except Einstein, who immediately understood its importance. Bose's method of counting quantum states of radiation showed that photons of a given frequency were indistinguishable. Einstein realized the importance of Bose's work. He calculated fluctuations in number of density of particles in very small volumes of a Bose gas. He found two terms, one that would be expected from the particle nature of matter, and another surprising term that implied a wave-like character. At once, he recollected having seen a doctoral thesis written by a young French scholar named Louis de Broglie, in which the possibility was proposed in analogy with dual nature of radiation. Einstein seems to have initially reserved his judgment on de Broglie's idea, but now, with his own calculations based on Bose gas, in a series of papers in which he explained Bose's counting method and its implication for material gases. Einstein described the importance of associating de Broglie waves with material gas using the formula lambda is S by mv or S by p for the wavelength of matter, and proposed molecular beam experiment to test the wave-like nature. At very low temperature, below a critical point, all the material particles of a Bose gas would condense to ground state of the system without any attractive force, only by virtue of their statistical property. Due to very low temperatures, the wavelength would increase, and these wavelengths would overlap with each other to such an extent that they would lose their individual identities and form one huge wave-like entities unlike anything known at the time, bizarre quantum state of matter. This came to be known as Bose-Einstein condensate. Eventually, on June 5, 1995, the first gaseous condensate was produced by Eric Cornell and Nicole Wayman at University of Colorado Boulder in NIST. It was produced in a gas of rubidium atoms cooled to 170 nanokelvins, a mere whisker about absolute zero. Soon after, Wolfgang Ketterle and his group at MIT produced Bose-Einstein condensate in a gas of sodium atoms. All three researchers were awarded 2001 Nobel Prize in Physics for their discovery. The fact that there are two classes of fundamental building blocks, bosons and fermions, rather than just one, has prompted physicists searching for unified theories of a particle to propose a relationship between two. This has become known as supersymmetry. If such symmetry exists, it would bring fermions and bosons together within the fold of a single family, and would imply the existence of a lot of undiscovered particles. This later could provide an elegant solution to many problem areas in standard model. In supersymmetry, each boson and fermion would have an associated particle named as a superpartner in other class. An electron, for example, fermion would have a superpartner called selectron, its bosonic partner. In perfectly supersymmetric theories, each pair of superpartners would have the same mass and internal quantum numbers except for their spin. To date, there is no experimental evidence that supersymmetry exists or that alternate extensions of the current models might be more probable. Particle accelerators specifically designed to study physics beyond standard model are required. The latest trend from upgraded Large Hadron Collider have cast considerable gloom in some camps of supersymmetry researchers. Bose also designed a special powder camera and a different thermal analyzer for analyzing the structure of clay minerals collected from different parts of India. The results were published by students A.K. Bose and Purnima Gupta in Nature in 1954. These efforts may not carry the stamp of his genius, but they show his dedication to building up a sound scientific culture in this country. A persistent lament among his country folk is that the man of Bose's genius could have contributed much more to science. There is also some residual discontent that he was denied the Nobel Prize while so many others got it, simply by proving he was right. Lev Landau, a great Russian physicist and a Nobel laureate himself, proposed a genius scale to rank smartest physicists of 20th century up to 1968. It was a logarithmic scale in which scientists he put in class 1 of rank 0.5 contributed 10 times more in his estimation than those in class 2. There are 5 classes. He put Einstein, of course, on top class 1. He put those who developed quantum mechanics the same class, where Bose also figures. Landau put himself in the next class. Cutting Einstein's appreciative postcard of July 2, 1924, Bose applied to the University of Dhaka for a 2-year study leave to visit European laboratories. Bose's main interest was in visiting leading European laboratories to learn firsthand the latest techniques, particularly in radiochemistry and X-ray crystallography, practices far away from his theoretical studies in quantum theory. His fame preceded his arrival in Paris, and so access was never an issue. But what transpired at his first meeting with Marie Curie was somewhat of a surprise. Carrying a letter of introduction from Paul Langevin, who was familiar with his work, Bose went to meet Curie with the intention of learning to work with radioactivity. I was allowed entry to a small chamber, Bose remembers. The great elderly lady sat there, dressed in black. I could recognize her from pictures of her that I had seen. I handed her the letter of introduction. She greeted me affectionately and said that there was no way she could disregard a recommendation from such a person. You will certainly get an opportunity to work with me, but not right now. After 3 or 4 months, get to know the language. Otherwise, you will find it difficult to work in the laboratory. You are in no hurry, I presume. She spoke at ease in chaste English for about 10 minutes. I had no opportunity to tell her that I knew a French of sorts already. I had been at it for the last 20 years at home. I came away resigned to carrying out her instruction. Bose spent the next 6 months learning X-ray crystallography and spectroscopy in laboratory of Maurice de Broglie, the elder brother of Louis de Broglie. He then returned to Curie's Radium Institute and worked there for a few months. His next destination was Berlin, where he arrived in October 1925. He sent a message to Einstein on October 8, seeking an appointment, but Einstein was not in Berlin at that time, and so they did not meet until his return. They met frequently thereafter and had wide-ranging discussions on physics and other contemporary issues of interest. There are a difference of opinion regarding the probability of interaction between matter and radiation. Einstein believing that spontaneous emission of radiation was an intrinsic property of atoms, while Bose saw it as consequences of new statistics. Einstein gave Bose a letter of introduction, which helped him gain the necessary privileges to borrow books from the university library and to attend physics colloquium. He also had opportunity to meet important scientific figures such as Fritz Haber, Otto Hahn, Hermann Mach, Lise Meitner, Polanyi, Richard von Mises, and Eugene Wigner. Both described the excitement in Berlin at that time. In a letter to Jacqueline Sadoc-Hahn, a physicist in Paris, he wrote, shortly after his return to University of Dhaka, Bose was appointed professor head of the Department of Physics and Dean of Faculty of Science. He set up using the knowledge of experimental science that he acquired in Europe to improve higher education and scientific research in his country, redesigning the laboratories and initiating the work in X-ray crystallography, spectroscopy, and crystal magnetism. He also worked extensively in chemistry, advising the doctoral students of his friend Gyan Chandra Ghosh, who worked on strong electrolyte and was often away from the campus, instead of plunging into theoretical chemistry for which he was well equipped. Both preferred to get his hands dirty, synthesizing and analyzing chemicals of contemporary practical importance. The inspiration possibly came from his father's small chemical works and his teacher Ray, the founder of the Indian chemical industry. Bose set up small chemical chemistry lab and encouraged students to synthesize amidine, sulfur drugs, and other drugs. Much of this research was never published, and few papers that did appear hardly ever carried his name. Bose was a polymath whose office at University of Dhaka turned into a center of free-flowing discussion on topics ranging from physics, chemistry, mathematics, statistics to literature, history, linguistics, and more. In his spare time, he would work out difficult mathematical problems. According to Karimanikam Srinivasa Krishnan, K.S. Krishnan, who worked with Raman to discover the Raman effect and who later joined the University of Dhaka. Dr. Bose furnishes pleasure in complex problems. His enthusiasm dies once he solves them. He throws proof in the waste paper, never bothering to send them to any journal. The 1940s saw an upsurge in Indian independence movement. The partition of Bengal into West Bengal and East Bengal, with Dhaka as its capital, was imminent. In 1945, Bose left Dhaka with a heavy heart to become the Khairat Professor of Physics at University of College of Science in Calcutta. He worked there until his retirement in 1956. In Calcutta, too, Bose developed his time to experimental science rather than theoretical physics. He set up an X-ray laboratory and encouraged organic chemists to determine molecular structure through X-ray analysis. He also worked on thermoluminescence and developed a novel rapid scanning techniques to study changing thermoluminescence spectra. This opened up fresh avenues for research in rapid continuous scanning. He reported the result from these studies in 1954 at Third General Assembly of International Union of Crystallography in Paris. In early 1950s, Bose suddenly returned to theoretical physics, and particularly to Einstein's unified field theories with great enthusiasm. He wrote 5 papers, 4 of them in French, in less than 2 years, solving difficult mathematical problems. These were his last scientific papers. Although they were all published in well-known international journals, none of them appeared in a
Time constraint.
yeah, Ferrari. In a, it is going to complete in a 2014 review of unified field theories. In 1955, Bose was looking forward to meeting Einstein again and discussing some new ideas with him during the international conference to celebrate 50 years of relativity in Bern. The conference was to be held in July, but Einstein passed away in April. Bose was working on new paper when news of Einstein's death reached him. According to eyewitnesses, he was silent for a while and then tore up the paper and threw it into the waste paper basket. Inspired by Rabindranath Tagore, a poet who had in 1913 become the first non-European to win the Nobel Prize, Bose devoted considerable time to promoting science in his mother tongue. In 1948, he set up Bangiya Vigyan Parikshad, an institution for popularization of scientific knowledge. After his retirement from University College of Science in 1956, Bose was appointed Vice Chancellor of Vishwabharati University, the institution founded by 1921 in Tagore. Bose served there only for 3 years, after which he was appointed National Professor of Physics in 1959. He was also given the Indian government's second highest civilian award, Padma Vibhushan, in 1954, and was sworn in as a nominated member of parliament in the upper house, Rajya Sabha. Bose's contribution to quantum theory was only formally recognized by foreign academies in 1958, after Dirac happened to visit Calcutta in 1954 and found that Bose had not yet elected Fellow of Royal Society. Dirac went back to England and pursued the matter. There is an amusing story about Dirac's visit to Calcutta, which Bose passed away on February 4, 1974. To perpetuate his memory, Government of India established the S.N. Bose National Center for Basic Sciences in Calcutta in 1986. As a fellow physicist, Binary Marker once observed, as long as there is light in the universe, there will be bosons everywhere. To conclude, the Indian presence of the prediction of boson particles are still more important in the history of science. When S.N. Bose described the light particles photons, he attributed them as particles with integer spin 1 with two components plus 1 and minus 1 for clockwise and anti-clockwise polarized light. When Einstein modified the manuscript of paper, Einstein did not approve the photon spin as described in the paper corresponding to RH and LH polarized light beam. The paper was published without mentioning the photon spin. If Einstein did not struck off the photon spin from paper, S.N. Bose could have been the physicist who introduced particle spin in quantum mechanics instead of Pauli, to whom the discovery of particle spin property is attributed, followed by exclusion principle. Had time supported S.N. Bose, then you could have been the discoverer of exclusion principle, and history of quantum mechanics could have been Bose's exclusion principle into Pauli's exclusion principle, renaming fermion particles as half-integer Bose particles. One should accept the fate of history of science just as the fate of human species. On this 2025 edition of National Science Day, one should remember Satyendranath Bose, who could have brought second Nobel Prize in Physics to India, but fate has its own design. With this note, let me conclude my talk and thank you for listening to my talk, and to IAPT for giving me this opportunity when nation celebrates the National Science Day. Thank you. Thank you very much.
Now it is time for discussions. We are already late. Anyway,
I'm very much thankful to the IAPT and will like to answer if there are any queries.
So one question, sir.
Yes.
Sir, even now we are teaching the students that internal degree of freedom 2 is due to the polarization of light.
Yes.
In many textbooks, it is said that it is polarization, but you are it is actually polarization of the spin, not that.
That is all the contemporary textbooks which follows that of Einstein's modification. But what I feel is that at least as an addendum, we should clarify the students that it was the photon spin which originally Satyendranath was predicted.
But we say it is transverse and longitudinal polarization.
Yeah, right.
Not RH and LH.
Yeah, that's right. Okay.
Is that right? Also, is that right?
No, essentially that it is essentially come from right hand and left hand polarized light. Right hand polarized light. Just like a electron spin, anti-clockwise and clockwise. What I feel is that this part of history also should be part of the students' syllabus, so that they should not forget about the unforgotten heroes of our science.
Sir, is that graviton has been discovered yet?
Gravitons have indirectly been discovered in the sense that we have a gravitational field, and the property of gravitational force is actually not a force; it's an emergent property of the geometry of space-time, and when the geometry of space-time is quantized, then the quantum of space-time is the graviton, which carries the so-called gravitational force. Actually, it's an emergent property. So the whole property of gravitational interactions can be remodeled with that, and Tanu Padmanabhan have done a lot of work in this direction. Thank you.
Oh, thank you, sir. Thank you.
So
Yes.
may I ask a question?
Yeah, please, sir.
I am Dr. Aluwalia, President IAPT, sir. And
Yeah.
thank
Yes,
you very
yes.
much for your
Yes.
wonderful
Thank you.
talk.
Thank you, sir.
I have one question in my mind.
Yeah,
If I look at the history as you narrated also in the presentation today,
Yeah.
Planck's derivation
Yeah.
actually was in a way till Bose came on the scene,
Yeah.
a kind of ad hoc derivation.
Yes.
Till he came and he brought a completely, there was a paradigm shift in looking at the things.
Yes. Exactly.
He really didn't bother about that there are oscillators. He
Yes,
only bothered
yes.
about
Yeah.
that there is a gas of photons inside.
Yeah.
So in a way, the basic understanding of the black body radiation
Yeah.
came to an end with the derivation of the
Boses.
Bose.
Yeah. Exactly. Yeah.
And what we think, and I would like to have your views on that.
Yeah.
Don't you think that Planck's constant should be called a Planck-Einstein-Bose constant?
Exactly.
On
That is what I mean. It should be renamed as Planck PEB constant.
Yes,
Planck
yes.
Einstein Bose constant.
So do you think that we should make a kind of a effort
Recommendation.
for that
Yeah.
at the international fora?
Exactly. Sure.
For example, in International Union for Pure and Applied Physics, where such
Exactly,
matters are
yes.
actually discussed.
If it's possible, it's wonderful.
So thank you. And sir, I would like to tell you one thing more.
Yeah.
That in one of our PER lecture series,
Yeah.
Professor Carl Wieman was one of the speakers on physics education.
Yes.
And we were very happy that he agreed without any fuss to give a lecture to the Indian audience.
Okay.
And we came to know that he donated whole of his Nobel Prize money for establishing virtual labs.
Yes,
which
exactly. Yes.
Handy for doing practicals during COVID time, which was a very, very trying time.
Yes.
So thank you very much, sir.
Sir,
We enjoyed it.
one more thing. To teach the students, especially light and mechanics, I developed a kit which does not have much cost, which contain about 100 experiments in optics and mechanics, including Kepler's laws and sun setting and sun rising. And for this, I usually go to schools to demonstrate it and donating some of the kit to the students. And for this kit, we got International Award of SPIE, first best educational kit. One day I also will share on this aspect of physics education.
Yeah, sure, sir. I think it's a wonderful observation which you have made.
Yeah.
And maybe we would love to have your collaboration with IAPT in propagating that kit also.
Yes.
Because we have that agenda. We want to really go ahead with this. Yeah. And let me tell you, sir, that we have a magazine which we are publishing now, which is a newsletter kind of a thing called Anveshika Buzz.
Oh.
And maybe you can serialize your experiments in that in a very interesting manner.
I have not seen it. I am getting IAPT bulletin, but
Anveshika, this started only 2 years back, and now it has stabilized, and we will try to share that with you.
Okay, please.
Thank you. Thank you very much.
And in future program, I also would like to talk on Kerala School of Mathematics, famous like that is Sangamagrama Madhavan of 14th century, who studied so many important problems in formulas.
We will make arrangements, sir.
Okay, please, sir. Thank you.
So
Sir,
because
can I ask a question?
Yeah, please. Yes.
Sir, you just told us about the Bose-Einstein condensate.
Condensate. Yeah.
I'm a physics teacher
Yeah.
working in a high school. So
Yeah.
can you please explain us how we can teach, how we can explain this Bose-Einstein condensate to the students in
Okay.
a simple
I will give you a simple explanation for high school students. They already know that matter wavelength lambda is h by p. Lambda
yes.
is h by p, h by mv, right?
Hmm.
And from
Yeah.
that, half mv squared is 3 by 2 kt, kinetic energy and like
Hmm.
that. So that you can write lambda as proportional to 1 by root of 2 pi kmt, temperature.
Hmm.
Right?
Yes.
As temperature goes to 0, lambda tends to infinity.
Yes.
So all the particles will have almost infinite wavelengths.
Yes.
Right? So they overlap. Once they
Okay.
overlap, their individuality is lost. They all behave like a single atom of a infinite wavelength. That is Bose-Einstein condensation. That's the simplest way
Okay.
of.
But at the high school level, the Planck's constant and other things have not been introduced, sir.
No, I think in 10th standard, 11th and 12th, they have that Planck's constant.
11th and 12th, all right, but not in high school before 10th standard.
10th standard, I think it is there.
Actually, I am in a higher secondary school. I also teach 11, 12 students. So it is useful for 11, 12 students. Yes.
Sure.
Thank you, sir.
Thank you.
I think we can conclude the session.
Okay, sir.
It is high time for us to start the next session.
Okay,
so it was a very illuminating talk, and he has broadly talked on S.N. Bose's contribution, his life, and everything. So let us thank Namburi sir for his.
Can I conclude, sir?
Yes,
please,
sure.
please.
Okay. Sir, Namburi sir.
Yes.
Thank you very much for this very brilliant talk.
Thank you.
And actually, it was like watching a movie or listening to a story by our grandma. It was actually you are not only an experimental physicist. As far as I know, we are an experimental physicist.
Yes.
You are not only an experimental physicist, a theoretical physicist, but you are also a historian, physics historian, or a scientific historian.
And also on brain modeling through EEG.
Okay. Thank you for everything, sir. Thank you for this nice and very interesting talk, very illuminating talks.